So today our lesson is going to be on titrations. And a titration is used to determine the concentration of a solution by using a known standard. All right, and remember brackets mean concentration, and this is solution. All right, our abbreviation for solution. So if I have a substance and I do not know the concentration, I can do a titration by using something that I know in order to figure out the unknown. All right, and this is really helpful. For example, at a former school that I worked at, when I got there, we found some solutions in the stock room, and they had not been labeled with the concentration, and so I didn't know what the concentration was. So what I was able to do is I just did a quick titration. I knew what the sample was. It was labeled with the date it was made. The concentration had just come off of it. So I just did a quick titration, and I was able to figure out the concentration of it and then go back and label that stock solution, all right, so that we knew what it was. So titrations are really useful. All right, a vocabulary term. Equivalence point. The equivalence point is where the mole of acid equals the mole of base. And this is not necessarily the concentration, it is the moles, because remember, from a previous problem or video, we did some examples where we had to go through and do a stoichiometric relation because there was a 2-to-1 ratio of acid or 2-to-1 ratio of base. So it's not the concentration, it's the moles. If we were to mix a strong acid, which I'm just going to write SA for strong acid, with a strong base, which I'm just going to write SB, we're going to end up with a titration curve that looks something like this, where the equivalence point will have a pH of 7. Now, we've learned in our reactions unit that an acid and a base neutralize to form a salt plus water. What we're talking about there is a strong acid and a strong base, meaning neutralize with a pH of 7. What if I did a strong acid with a weak base? In this case, I still start acidic, but as I add base, it neutralizes those hydrogen ions. All right. And I end up with an equivalence point that is below 7. So at some point, my moles of H plus or acids equal my mole of base, but the overall pH is going to be below 7. Now let's think about this, all right? If I do a strong acid and a strong base, both of these go 100% to completion. So I have 100% H plus and 100% OH, so my pH is at 7. Here, I have a strong acid that goes 100% to H plus. A weak base only produces some hydroxide ions. So my strong acid goes to completion, bringing my pH at equivalence point below 7. All right, I have a strong base and a weak acid. All right, so in this case, I start out basic. And as I add acid, I get more and more acidic. And my equivalence point here is going to be above 7. So my pH is right here on the y-axis. So this is my pH. Okay. And this is the volume added. All right, so if I start with a strong acid, then I am adding a strong base. So this would be the volume of base. If I start with a strong acid, I'm still adding a base. So this is the volume of base. And if I start with a strong base, I'm adding an acid, so this is the volume of an acid. And this is kind of where we're going to stop until we get to the AP portion of this course. All right, I need for you to please understand that a titration is going to add, if we come back here to strong acid, strong base, I add base, and as I add base, I start to get rid of the hydrogen ions. My pH becomes less and less acidic until I reach equivalence point. And then as I continue to add base, I now become basic. My strong acid, as I add base, again, I become less and less acidic. Once I reach my equivalence point, as I continue to add base, the pH then becomes basic. My base, I start basic. As I add an acid, I become less and less basic until I reach equivalence point. If I continue to add acid, my solution will then become acidic. So this is what you need to know. We are only going to calculate strong acid, strong base. The calculation part of the week is going to come in the AP portion because that's a little bit more intense and a little bit more we need to know a little bit more information that we don't currently know in order to do calculations here. So I need you to understand the concept of these 3 different titrations, but we're going to stick to calculations of only a strong. So our formula for a strong is the molarity of an acid times the volume of an acid will equal the molarity of a base times the volume of a base. So this is MAVA equals MBVB. All right, and let's take a look. Let's say what volume of 0.001 molar sodium hydroxide is required to neutralize a 25 ml sample of a 0.110 molar hydrobromic acid. Okay, so the molarity of the acid is 0.110 molar. The volume of the acid, I had 25 mils of that. The molarity of the base is 0.1. And we want to know the volume. So how much sodium hydroxide do I have to add? So when we plug this into our calculator, and we're going to stick with the rule of 3, we end up with 27.5 milliliters. If 35.4 milliliters of a 1 molar hydrochloric acid solution is neutralized by 67.3 milliliters of barium hydroxide, what is the molarity of the barium hydroxide? All right. So The molarity of the acid is 1 molar times the volume of the acid is 35.4 mils equals the molarity of the base, which is what we are trying to find, times the volume of the base, which is 67.30. All right. And now we have to be really careful here because we have been provided barium hydroxide. So barium hydroxide has a formula of BaOH2. So I have 2 moles of barium hydroxide. 2. So when I solve for my molarity of the base, I end up with 0.526 molar. However, I have 2 moles of hydroxide. Hold on. And a base is OH, okay? For every 1 mole of the entire thing. So when I plug that into my calculator, I get 0.263, sticking with the rule of 3, molar. So if it is not a 1-to-1 ratio, you have to then go and do your stoichiometric relationship. There are 2 moles of hydroxide for 1 mole of the entire compound. Let's do one more problem. If 133.73 mils of a standard solution of potassium hydroxide and it has a concentration of 0.298 molar, exactly neutralizes. Okay, so we're at our equivalent point here, exactly neutralizes 50 mils of a diprotic acid. What is the concentration of the acid? So we have to do our MAVA equals MBVB formula. So that's going to be my concentration is what I'm looking for. So that is my MA. 50 mils of that acid was diluted or was used, excuse me. The concentration of my base is 0.298 molar, and the volume is a 133.7. So when I solve for this, my MA is going to be 0.797, And this is an acid. So my moles of acid go on bottom to my moles of the entire acid, which we don't know what it is, but we know it's an acid. Okay, it didn't tell us which acid. It doesn't really matter. It is a diprotic acid, meaning there are 2 moles for every 1 mole of the compound. So when I solve for that, I end up with, using my rule of 3 here, 0.399 molar. So you have to do your stoichiometric relation. If this was a 1-to-1 ratio, it was a monoprotic acid, and potassium hydroxide, this is KOH. Yes, KOH. So that is a 1. Okay, but this is a diprotic, so we have to do that relationship. Very important to be careful there.